How did we came to know that in photosynthesis there exists two photosystems? Answer lies in the Emerson effect. This is Dr. Pankaj Kumar, your mentor for today's sessions. So what happens, Emerson was studying the photosynthetic yield of chlorella, and for this what he has done, he has given a monochromatic beam of light. Okay, and after giving a monochromatic beam of light, the photosynthetic yield was calculated. Now what he observed, that as the wavelength increases, the photosynthetic keep on increasing, okay, starting from the blue region to red region, right? But beyond the red region, there was a sudden decrease in the photosynthetic yield, right? And this yield was referred to as a red dwarf phenomena, okay? So the answer that why this actually it falls, he did another experiment and what we call Emerson enhancement effect. And for this what he did, he has given a two wavelength of light simultaneously, one of shorter wavelength, another of longer wavelength. So when the two superimposed beams of light was given, it was observed that photosynthetic yield was much greater in comparison to if both light were used individually. Okay, for instance, if you see over there, then what you see, that this is the photosynthetic yield for 680 nanometer and this is for the 700, that is for longer wavelength and that is a shorter wavelength. If we sum up, then only we won't be able to get the total amount of photosynthetic yield what we got when we are using simultaneously. Okay, as a result of the simultaneous use of longer and shorter wavelength of light, there is an enhancement in photosynthetic yield, and this enhancement was referred to as a Emerson effect, right? So what was the net conclusion? The net conclusion was that photosynthesis itself consists of the two photosystem, that is photosystem 1, which is actually being controlled by shorter wavelength of light. So what is the net conclusion? The net conclusion is that there exists two photosystems. One operate in the longer wavelength and another operate at the shorter wavelength. So photosystem 2 operates at the shorter wavelength, and the reaction center for photosystem 2 is P680, and photosystem 1 that operates on a longer wavelength, and the reaction center what we call P700, right? One more thing, why there was a drop in the photosynthetic yield in case of red dwarf phenomena? Because as we increase the photosynthetic, as we increase the wavelength, what happens? That one of the photosystem is actually getting out of range. So the question is asked that which photosystem is actually get deactivated in the red dwarf phenomena. Answer lies is the photosystem 2, because we know very well that photosystem 2 works at the shorter wavelength of light, right? So PS2 or photosystem 2 is deactivated during the red dwarf phenomena. Okay. Now let's talk about that what are the two different types of reaction center or photosystem. So PS1 or P700 and PS2 or P680, these are the two reaction centers, right? And you know, PS1 is located in both granule as well as stromal lamellae, and it mainly consists of chlorophyll A. Chlorophyll B is also present, but in a very lesser amount. Okay, so larger quantity is of the chlorophyll A, right? And here the accessory pigments are comparatively very less, right? But the moment we talk about the PS2, in case of PS2, that is located only in the granule lamellae, not in the stromal lamellae. Okay. So it is also made of chlorophyll A and B, right? But here the amount of B is comparatively more. Okay. So if I compare chlorophyll A and B, even in that case the chlorophyll A is more. But if we compare with a PS1, that here certainly chlorophyll B is more. Okay. And it is associated with the photolysis of water, right? So this is how we can differentiate between photosystem 1 and photosystem 2, right? Very quickly, let's discuss about photosynthetic unit. You know, photosynthetic unit consists of antenna molecule, we also call them LHC or light harvesting complex, and the reaction center, right? Just now we have seen the reaction center, that is PS1 and PS2. Now let's acquaint ourselves that what exactly is the photosynthetic unit. Okay, you see, the photosynthetic unit consists of 300 photosynthetic pigments, right? Out of those 300, 240 is a chlorophyll and 60 is a accessory molecules. Okay, so you can see there is a 240 chlorophyll molecule, right? The very function of antenna molecule is to harvest light energy, and after harvesting it channelize the reaction center for the further excitations, right? So once the energy reaches the reaction center, then it is followed by the photochemistry, in which what happens, the electrons are expelled to the higher level and thereby energy is released, and those energies utilized for the photosynthetic activity. We will discuss later on this sessions. Okay. In the diagram itself you can see there that this is the reaction center and it is associated with a LHC. Okay, and the LHC, what happens, that the pigments are arranged according to increasing absorption spectra. What is the advantage? We will discuss about that. So first thing, pigments are arranged according to increasing absorption spectra. In order to understand the advantage, we need to understand the two phenomena, one what we call fluorescence and second what we call phosphorescence. Now just see what is fluorescence. In case of fluorescence, what happens, suppose this is a photosynthetic pigment, and if I give a light of, let it be say lambda, and if a lambda dash is actually coming out, right, then what will happen, that lambda dash will be greater than lambda. Okay, so wavelength is going to increase the moment any light is passing through the photosynthesis. Okay, so in case of phosphorescence, what happens, if I withdraw this light, it is going to be immediately withdrawn. Okay, and it is operate between the accessory pigments and the reaction center, right? So these are the accessory pigments and the reaction center. So all the photosynthetic molecules that is present in the LHC is going to show the phenomena of fluorescence, right? Now what is the advantage? Just try to understand like this, that suppose if I draw a reaction center or photosynthetic unit like this, and let it be this is a reaction center, okay, and photosynthetic pigments are arranged according to increasing absorption spectra, right? And suppose this light has a absorption spectra of 500 nanometer. Okay, so naturally it is increasing, so thereby let it be say it is a 550. So what will happen, this molecule will absorb a light, it will emit a light which will be of greater wavelength. Right now we have discussed it is of greater wavelength. So once it is a greater wavelength, naturally it will fall in the absorption limit of the adjoining pigment. Okay, similarly this is also going to emit light, but this is also going to emit with a higher wavelength. So naturally it will fall on the molecule nearer to the reaction center, and thereby one-way channelization of energy from periphery to the center is going to happen. So that is the advantage, that why the molecules, how the molecules are arranged into the increasing absorption spectra, right? One more thing, you see, phosphorescence occurs beyond the reaction center. Okay, and the very thing in phosphorescence is that when you withdraw the light, even for a very fraction of second, light keep on emitting. The photochemistry behind phosphorescence can be explained like this, that we know very well in chemistry you might have read that electrons are normally present in a anti-spin manner. But in phosphorescence what happens, that electrons are present in a same pin. Okay, so if I give a light, what will happen? It will remain the same pin. So the light will keep on emitting. So if I withdraw, then what happens? Some fraction of second will be taken by this, that to come its the original position, right? It will come its the original position. And for that fraction of time, what will happen? The lights will keep on emitting, right? This is what we call phosphorescence, and that occurs in the reaction center and beyond. Okay. One another interesting thing. Chlorophyll shows a phenomena of fluorescence and phosphorescence, right? But the energy is actually being transferred by a process called inductive resonance. Now, inductive resonance is what? That the molecule in a very space is going to vibrate, and as a result of vibration, they are going to transmit energy. So, two things. Chlorophyll shows the phenomena of fluorescence that gives them an advantage of one-way channelization of energy from the accessory pigment to the reaction centers, but the mode of transfer of energy is always inductive resonance, right? Let's discuss one more thing, and that is what happens during the excitations of the pigments. You know, for blue light, what happens when it absorbs, chlorophyll absorbs blue light, then electrons are expelled to the higher orbit. So since blue light has a greater amount of energy, what will happen? It will expel it not only to the excited state, but one stage above what we call singlet stage. Okay. So when the electrons return to its ground state, it releases energy, mostly in the form of heat, and those heat has a capacity to photo oxidize the chlorophyll, in a technical term what we call solarization. Okay, but this is actually prevented by the carotene, right? So once it comes down, then what will happen? That it is going to release a delta energy, right, delta E, and that is utilized for the photosynthesis. Okay. So what will happen in case of red light? You see, in case of red light also electrons are expelled, but only up to the excited state. Okay, and once it goes down the ground state, when it regains the ground state, that is also going to release the delta energy, and that is utilized for the photosynthesis. Okay, so in both cases photosynthetic yield is same, right? But why we are calling red light is the most efficient? Because in case of red light there is a no loss. What here see that in blue light there is a loss of energy, but in case of red light there is a no loss of energy. So that's why we say red light is the most efficient light for photosynthesis, right? So this is how we can say that red light is the most efficient, and that's all as far as today's session is concerned, right? Thank you.